Let's consider then a linear multi-port microwave device. So in this case, I have a 4-port example here. Inside is a circuit made of linear components, inductors, capacitors, resistors, links to transmission lines, and the like. And because of that, we can fully characterize it using things like impedance matrix or admittance matrix. In this case, we're going to introduce a new way of characterizing a linear multi-port device, and that is by using the scattering matrix. Now notice in this case we've connected transmission lines to all 4 ports, and we've left the characteristic impedance values indeterminate. They could be all the same, or they may be all 4 different, or 2 of them may be the same and the other 2 a different value. What we're going to do to characterize this is consider then the 2 propagating waves along these transmission lines. And so there is a plus going wave, which is incident on port 1, and a minus going wave, which is exiting or reflected or scattered from port 1. And so that's what we have. We have incident waves on each of the ports, and we have scattered waves that come out each of the ports. So we're going to go through and characterize the device based on these incident and scattered or reflected waves. It's important to note in our notation that the incident waves, the waves propagating toward the port planes, are the plus waves. And because of that, it must mean that the index z that we define along each transmission line must be increasing as it moves toward the port plane, as it moves toward the device. And so the index z we have for the scattering matrix cannot be arbitrary for each of the 4 ports. It must be increasing as we move toward the device itself. Likewise, for each port of the device, we need to define a location on that index that defines the port plane. And so this is the boundary between what is considered to be part of the 4-port device and what is considered to be simply the transmission line that is connected to it. And that can be an arbitrary delineation between those 2 values, but it needs to be specifically and unambiguously made in terms of some value. Yes, oftentimes the index is set to be 0. The location of the port plane is the index z is equal to 0, but not always. So we want to be careful in terms of how we do that. Again, this is reminiscent, or at least it should be, of the things that we did with respect to the impedance matrix and the admittance matrix. We showed a schematic like this, for example, for the impedance matrix, a 4-port microwave device, and we went through and we showed how we could relate then the currents at each of the ports to the resulting voltages at each of the ports. We wrote it as if the voltage at each port was a reaction due to the current at all of the other 4 ports, and that gave us the transimpedance parameters. Now, one thing in this notation is that we define positive current at each of the ports to be current flowing into the port. Positive current was flowing into the device. And so this is very much like we have had to do for the index of each of the transmission lines. For the scattering matrix, the wave propagating toward the device is the plus wave, is the positive wave, the incident wave on those ports. Now, we went through and we found from the transimpedance parameter the impedance matrix. Likewise, for the admittance matrix, we found the transadmittance parameters, and they fully characterize the device. Again, we can think of this as sort of a matrix version of input impedance. For a single port device, we have an input impedance. For a multi-port device, we have an impedance matrix. Same thing for admittance. Single port device, input admittance. Multi-port device, a admittance matrix itself. So the scattering matrix, we're going to go through and characterize the device not by relating the current at one port to the voltage at the other, or the voltage at one port to the current at the other. We're going to relate or describe this device by relating the incident wave at one port to the exiting or scattering wave at the other. And the relationship between an incident wave on port 1, let's say, and the scattered wave on port 4, that relationship is going to be one of our scattering parameters. And for the case of a 4-port device, we have 16 different scattering parameters, just like we have 16 different transimpedance parameters. And we're going to form those scattering parameters into a matrix, a 4x4 matrix that we call the scattering matrix. And when you think about this, this is similar to taking our input reflection coefficient of a single-port device and now expressing it as a matrix form for a multi-port device. For the input reflection coefficient of a single port device, it's the ratio of the exiting or scattered wave divided by the incident wave on that port. Now we're going to have these trans reflection coefficient parameters, essentially these scattering parameters, which relate the wave exiting or scattered from port 3, for example, to the wave incident on port 1, for example. And so by doing so, for all possible combinations, 16 of them in this case, we are going to fully characterize this device and place those values into a matrix we call the scattering matrix. Yet another way of fully characterizing a linear time invariant multi-port device. A mistake that's commonly made among students and sometimes electrical engineers is to say that or think that the scattering parameter that we define is going to be a relationship between a incident voltage, plus wave voltage, as a function of position z, to the minus wave voltage. And that's not exactly correct, because this value, the scattering parameter value, is going to be a complex number. It's not going to be a function of position z. And so it doesn't relate this function of position z to this function of position z. What this number does is relate two different numbers, two complex numbers. Each depend on the plus and minus wave voltage, but still are numerical values. And let's see what those are. So say that there is a single incident wave on a multi-port device. On this 4-port device, let's say that wave is on port 1, one incident wave. The incident waves on the other ports are equal to 0. Now we'll talk about why that needs to be and how we can make that happen here later. But let's just say there's one non-zero incident wave, V1 plus. What we're going to do is take that wave and we're going to evaluate that wave at one location on our transmission line. And that location on the transmission line is at the index that defines the port plane for port 1. Remember, this has to be a number. Oftentimes it's 0, but it doesn't have to be. So the important thing here is to take your plus wave expression as a function of position z and evaluate it at one location, at the port plane, which then takes a function of position z and turns it into a complex number. All right, so this needs to be a complex number, and I emphasize this because oftentimes students will write down the incident wave with respect to index z and won't evaluate it at the port plane, and they end up with a scattering parameter, which is a function of position, which, you know, that's like having an impedance. That's a function of transimpedance parameter. That's a function of position. They have to be numbers, and to get numbers, we evaluate them at the port plane. We did this before with the impedance and admittance matrix. Remember, we took the total voltage at the port planes and the total voltage at the port planes. Okay, so again, we're going to say we have one incident wave. In our example, it's the wave incident on port 1. Because we have a wave incident on port 1, we have a wave that's carrying energy into our 4-port device. It is certainly reasonable to expect that we would then have waves exiting the other ports. That energy is coming out of the ports. Something gets into port 1, what comes out of the other ports? What comes out of port 2, what 3, 4, and even port 1 itself. 4 exiting waves, 4 scattered waves, and we say that those are the result of the single incident wave on port 1. Port 1 incident is the cause, scattered waves at the other port are the results. And so we're going to compare those two. Again, we need to compare numbers, and so we don't go through and look at the exiting waves or the scattered waves at every port only. We go through and look at the scattered wave, let's say at port 3, and we evaluate it at the port plane. So if we know the minus wave voltage along this transmission line, we know the value, the wave amplitudes, and we can express it specifically either by evaluation or measurement. Then we go through and take that function and we evaluate it at one location, at the location for port 3. Now we have a second complex number. The first complex number is the value of the incident wave at the incident port plane, and the second number is the value of the exiting or scattered wave at its port plane. For the example, we had a incident wave at port 1, and we have an exiting wave now at port 3. That should be the complex ratio between V1 plus, not V3 plus there. There should be a 1. And so we go through here, V3 minus at the port plane of port 3, V1 plus at the port plane of port 1, two complex numbers. Now, we're going to go through and take the ratio, but we're going to do something else. We're going to take the ratio now of the square root of the characteristic impedance. Where is this going? And in this case, we have the square root of Z01, which is the characteristic impedance of the incident wave. It's in the numerator. And then the square root of the characteristic impedance of Z03, that of the scattering wave. It's in the denominator. Why do we write it this way? We have V3 here in the numerator. Why do we have Z01 in the numerator? Seems like they should be flipped over. But no, these are right, because let's go through and rearrange them in this way. And so when we do that, what we see is V3 minus divided by the square root of the characteristic impedance that it's propagating on the transmission line. And of course, we recognize that, hopefully, as the new normalized wave function B. And this, since it's propagating on the third transmission line, the third port, we're going to give it the subscript B3. And so this is the value of our normalized wave B3 evaluated now at the port plane. Remember, B was a function of position Z. Now we're going to evaluate it at one location, index, to determine a number. The same thing for the second term. This is simply the inverse of our new normalized wave function that we call A. A is an incident wave, incident in this case on port 1, and so we call it A1, or we should have called it A1. Again, that's a typo there. I'm sorry, this is all messed up. That should be A1, and Z1 is equal to Z1P there. This is the, yeah, this should be, these should be all ones at that point. I apologize for that. So that's B3 divided by A1, and that gives us the scattering parameter of S31. Well, I botched that previous example so badly. Let's do a different one. Let's do S21 instead. S21, that scattering parameter, is going to be the ratio of the scattered wave, the exiting wave at port 2, divided by the incident wave at port 1. And again, we have now a ratio of the square root of the characteristic impedances. Again, V1 down here in the denominator, but we have the square root of Z01 here in the denominator. And when we do that, we find we get these terms. We recognize this as an exiting wave, a scattered wave, a wave going in the minus direction. In other words, a normalized B wave. We'll give subscript 2 since it's propagating the direction or it's propagating on the port 2 transmission line, and we evaluated it index at the port 2 port plane. This term turns out to be, of course, the incident wave I was seen before, the normalized incident wave, so that's A1, and here I have got my numbers correct, all right? So B2 evaluated at the port plane of 2, and A divided by A1, the incident wave evaluated at the port plane of port 1. We could also go through and define, let's say, the scattering parameter S34, all right, S34. The way this works, 3 is the port at which the scattered wave is coming out. The second value, 4, then is the port where the wave has the incident wave coming toward it. And so S34 then would be this value here. It would be the value of B3 evaluated at the port plane of 3. Again, this S34, 3 is the exiting wave or the scattered wave there, so it's B, and then 4 is the incident wave on port 4 evaluated at that port plane. And we can relate this again to the plus and minus wave voltages at port 3 and port 4 as well. Again, don't leave this ratio of the square roots of a characteristic impedance out. Oftentimes, students will leave this out, and engineers will leave these out. And notice that if the characteristic impedance of the two transmission lines were identical, they would cancel, and so we would get the right answer regardless. But I want to leave these in. They'll force you to go through and make sure you understand that this becomes one only if these are equal to each other, because we'll have many examples where the characteristic impedances at the port planes are dissimilar from each other, and we need to define the scattering matrix in this way in terms of our normalized wave amplitudes, our wave normalized propagating waves, in order to get the correct answer. So to fully characterize a multiport device, we would go through and try to find every relationship, the relationship between the incident wave on one port, again, only when only there's an incident wave on that port, to the exiting wave at all other ports. Again, to really make this useful to us, we have to make sure there's only one incident wave. What we're trying to say is when we have a wave exiting port 2, it is due to the wave incident on port 3, for example. Well, we can only say that if there is only a wave incident on port 3. If energy is coming in from some other direction, then of course we can't make the direct connection between those two values. And so if we go through and find every relationship, every scattering parameter between the incident wave at one port to the exiting wave at the other, or the scattered wave at the other, if we do all of them, we will end up with n squared number of scattering parameters. In the case of a 4-port device, we have 16 scattering parameters relating the incident wave at each of the 4 ports individually to the scattering waves at each of the 4 ports due to each of those individual incident waves. All right, so let's come up with the general form of a scattering parameter. So we have SMN. M and N can be equal to each other. We can have S11 and 22 and 33. Generally speaking, they'll be different, S31 and S42 and the like. But we define them then as the ratio of the normalized scattered wave at port M to the normalized incident wave at port N. And again, this is the important thing. One of the most important things is that's true only if there is one and only one non-zero incident wave. And that incident wave, of course, must be at port N in order to have a value of A that is non-zero. So the A's are all 0 except at port N, and then we determine the scattered waves at each port due to the value incident wave at port N. We determine that it's scattered wave at port M. Again, it's scattered wave, exiting wave, so we call it B in the direction of decreasing Z. And take the ratio of the two. So again, scattering matrix is defined as the ratio of the normalized waves at 2 different ports when only one port has a incident wave that is non-zero. And of course, that must be the value associated with this port N where A is non-zero. Oh, one extremely important point in all this. Again, we go through and rewrite this in terms of V minus and V plus, and we see this ratio of the square root of the characteristic impedance. And we see, well, that's because of the normalized complex waves that we defined here. But this is a really important thing to point out. What this says is the scattering parameter of a device, and thus the scattering matrix of a device, depends on the characteristic impedances of the transmission lines connected to it. Now, this is completely different from what we did in the impedance matrix and the admittance matrix. There, the impedance matrix and admittance matrix depended on the device and the device only. Everything in that blue box, that's what determined those transimpedance and admittance parameters. But for scattering matrix, what it does is characterize the device in the blue box, but also it depends on the transmission lines connected to it. It says what will happen if I take this blue box and I connect transmission lines to it of specific characteristic impedances. And so it's a characterization both of the device and the transmission lines connected to it. What this means is if I take a blue box and I connect certain transmission lines, let's say they're all 50 ohm characteristic impedance, and I determine or measure the scattering matrix for that device, and then I keep the box the same device. I'm going to disconnect the transmission lines and I'm going to connect new transmission lines to them. And in this case, let's say the characteristic impedance of those transmission lines now are half of them are 50 and the other half of them are 75. What we'll find in that case is that we have different values for our scattering parameter, different values for our scattering matrix. The scattering matrix characterizes the device itself in terms of the transmission lines connected to them. They all have to be evaluated together. And again, if we change the transmission line characteristic impedances without changing the blue box, we will still, or the circuit itself, we will end up with different scattering parameters in that case. So we might ask ourselves, how do we ensure that there's only one incident wave on a multi-port device? We had the same problem before with impedance matrix, right? We said, well, we have to make sure that there's only one non-zero current on one of the ports, that the current on all the other ports must be equal to zero, except for the one non-zero current that we are evaluating. How do we ensure that the currents at the other ports are equal to zero? We said, well, that's easy. We simply attached open circuits. Either in the lab we attach open circuits, or in schematically we attach open circuits if we're evaluating it schematically to determine the impedance matrix. Likewise, for admittance matrix, we said that the voltage at all ports except for one must be equal to zero. Well, how do we ensure that the voltage at those other ports are equal to zero? Well, that was easy. We simply attached a short circuit to those ports. Again, either physically in the lab if we're trying to measure it, or schematically if we're doing the analysis for the impedance or transadmittance parameters, we connected short circuits at those ports. We're going to do the same thing here for scattering matrix. How do we ensure that the incident wave at all ports except for one are equal to zero? How do we make sure that there is no incident wave on port 2, for example, or port 3, or port 4? Well, what we can do is go through and terminate then these transmission lines connected to each of these ports. We can terminate it with a matched load, quote-unquote matched load, a resistor that's numerically equal to the characteristic impedance of the transmission line itself. And of course, the load reflection coefficient for a matched load is equal to zero, which means we have a situation now where the reflected wave off this must be equal to zero. This is a passive device. It can't generate a wave from it. All it can do is create a wave from it that is reflected once it reaches there. But by making gamma L equal to zero, we will have no reflected wave. Nothing can reflect from this load, and therefore there'll be no wave propagating in this direction. There'll be no incident wave on port 2. The same thing for port 3, the same thing for port 4. So again, we have this commonality between our other matrices for describing a multi-port device. A impedance matrix, we go through and put open circuits on all but one port. In admittance matrix, we put short circuits on all but one port. And for the scattering matrix, we are going to put match loads at all but one port. Now, be careful here. If you go through and just simply look at your equations, you might be a little bit confused, because we say we put a matched load, terminate our transmission lines in matched loads, and that results in a load reflection coefficient of zero, and that results in a V plus wave, the plus wave being zero. This seems weird because when we looked at the terminated transmission line, just a simple terminated transmission line, when we had a load reflection equal to zero, of course it meant that the minus wave was equal to zero in most cases there. In this case, though, we say gamma L equal to zero will result in a plus wave being equal to zero. And again, this causes confusion. Students go back and look at their notes and they say, oh, it told me in this place that gamma L is equal to zero means V minus is equal to zero. So if I terminate all my transmission lines in matched loads, then V minus will be equal to zero. But that will lead you astray and lead you to the wrong answer. This is a case that demonstrates how you have to carefully look at an equation and the thing that it describes, the physical structure that it describes, to put the equation itself in context. The equation is always a correct description for the physical structure, but the physical structure may change from one application to another, and so you have to really put the equation into context, and that's what we have here. Earlier, we talked about a terminated transmission line. We have a situation where we show that if the load reflection coefficient were equal to zero, then there'd be no reflected wave. There would be a wave incident on that load, that passive load. If gamma L is equal to zero, there is no reflected wave, and that is absolutely true. In the case of the terminated transmission line, the incident wave generally was flowing in the direction of increasing z. Again, this is dependent on our index, and we can orient it any way we want. For the terminated transmission line, we generally made z increasing as we move toward the load. So the incident wave in this case was the plus wave, and therefore the reflected or scattered wave in this case was the minus wave. And so the result was the reflected wave is equal to zero. Oh, and the reflected wave happens to be the minus wave in this case because of how we did our index. And so that's why we came to this conclusion for this particular structure and this particular index. Contrast that with our current situation, where we've attached a transmission line to some port of a multi-port device, and we're trying to determine the scattering parameters for this multi-port device. So in that case, we must make the index z increasing as it moves toward the port. In other words, it's increasing as it moves away from the end of the transmission line, where now we've, let's say, placed a load, perhaps a match load, here at the end of the transmission line. So how do we interpret this? Again, we know a match load will reflect no wave. We have an incident wave on this load, nothing is reflected if gamma L is equal to 0. That physical statement is still true here. What is different is our index, and therefore what is different is what we call the plus wave and the minus wave. In this case, the wave that's incident on the load is the wave propagating away from the port in the direction of decreasing z. So this is the minus wave. Again, minus and plus depend simply on our index, which is arbitrarily determined. For scattering parameters, we have to write it, though, in terms of increasing z as it moves toward the port plane. So the minus wave is the incident wave on the load, and therefore the wave reflected from the load now is moving in this direction toward the port. That would be the reflected wave from the load. And of course, this is the ambiguity that comes into play when we talk about incident. Incident on what? The minus wave is incident on the load here at the end of the transmission line. The plus wave is incident on the port. Therefore, the plus wave is reflected from the load, and therefore the minus wave is reflected or scattered from the port. And so you have to go through and look at your situation and the index to be able to come up with the correct equation to express the idea that the reflected wave from a match load is equal to 0. So to summarize, if we have a wave that is incident on some load, and we evaluate that incident wave voltage at the location where the load is, and then we multiply it by the load reflection coefficient, that will give us the value of the reflected wave voltage at that same load. This is a statement of the physics involved. Now, how do we map the incident and reflected into plus and minus? Again, that depends on the situation, the structure. You have to go through and look at each circuit carefully and apply the underlying physical meaning of this equation. All right, so go back to our definition of a scattering parameter. We're going to write it again, similar to what we did before, with one little change now. The scattering parameter SMN is the ratio of the B wave, the scattered wave at port M, to the incident wave at port N, the normalized incident wave evaluated at that port N. And that's true when all ports other than port N now are terminated in match loads. Before we said when only port N has a wave incident on it, when all the incident waves on the other ports are equal to 0. Now we've enforced that condition by terminating the other ports in match load. We've connected it to the transmission line that is connected to those ports, a value which is equal to the characteristic impedance of whatever transmission line that is. And otherwise, mathematically, it's the same. So this phrase here is the important phrase, and the one that sometimes students forget. It's not that this is it's always BM over AN is SMN. It's only true when this caveat, when this condition has been met. So again, this is true. The definition is true if and only if all ports except port M are terminated in matched loads, or in other words, the only incident wave on any of the ports is that incident wave on port N. All the remainder of the incident waves are equal to 0. And this is very important. We can have a situation where we have multiple incident waves on a multi-port device, 2 or 3 different incident waves that are non-zero. Now we could go through and determine the incident wave on one of those ports, and we could determine the scattered wave value, normalized value at some other port there, and they would both be complex numbers. We could take the ratio of those two values and we get another complex number. But that complex number would not be the scattering parameter associated with the incident and exiting wave. Remember, what we're doing here is we're putting one and only one incident wave on, let's say, port 1, and then seeing what wave scatters out of port 3. What we say at that point is that the wave scattered from port 3 is due to the wave incident on port 1, and the ratio of those two gives us the scattering parameter. If we had an incident wave both at port 1 and port 2, and we would find that there would be, again, a scattered wave coming out of port 3, but we could not attribute that scattered wave completely to the incident wave at port 1 or the incident wave at port 2. We wouldn't really have any way, based on that observation, to make a judgment as to what is what amount of the exiting wave at port 3 was due to the incident wave at port 1 or port 2. The only way we can do that is to turn off the incident wave at all other ports except for the one at port 1, and that way we can say emphatically and without ambiguity that the wave exiting port 3 is due to the port incident port 1 and the port 1 alone, because that's the only incident wave there is. Note that I've made the definition of these scattering parameters as general as possible, and that therefore makes it as useful to us as possible. One of the things we frequently find is that the location of the ports, port 1, port 2, that index that we have is often set as 0. And of course, this makes things mathematically a little bit easier. Complex exponentials become a value of 1, for example. And so it is a common index. Again, I don't like it too much because it takes away the complex exponential and removes it from the mathematics when, in fact, physically it is very much there. If we do, though, have our port planes defined as the location on the index z is equal to 0, then we find that our scattering parameters simplify somewhat, because the value, of course, of the minus wave voltage at z is equal to 0, by definition, is the complex wave amplitude v0 minus. The value of the incident wave, the plus wave, at z is equal to 0 is, again, by definition, the complex wave amplitude v0 plus. And so oftentimes in scattering parameter definitions, they are defined simply as v0 minus and v0 plus. That is only true under the condition that the port planes are defined as 0. When they are not defined as 0, then this is not true. This is a very specific condition and can be used only for that specific condition. Oftentimes this result is used blindly, regardless of how the port planes are defined. And again, you have to be very careful. That's why I like the more general statement. You go ahead and insert the value of the port plane definition into the general form of the scattering parameter, evaluate it to get the value, as opposed to simply jumping to some recipe which may or may not have any validity to the problem at hand. Along those same lines, we often have a situation where the transmission lines connected to every port on a multi-port device have the same characteristic impedance. Frequently, this is 50 ohms. And so when we go and look at our general solution or general statement of scattering parameters, the square root of the characteristic impedances in the numerator and denominator cancel out. And what we're left with is, even though this is the general expression, we are left with this result here. Notice there's no square root of the characteristic impedance there. That's because they were equal to each other and they became a value of 1. Moreover, we could take the previous page and say if our port plane indexes are numerically equal to 0, then we get a value where this is equal to v0 minus divided by v0 plus for the two ports in question. And oftentimes, again, that is how scattering parameters are defined, and engineers and students alike will use those definitions blindly, even if they are not valid for the particular situation at hand. So again, I like the more general forms. You put in the values of the characteristic impedances. If it turns out they cancel out and are equal to 1, you're a very happy person. But if they don't, then you're going to get the right answer, where someone who simply uses the lookup recipe is going to get a completely erroneous result. So the question is, what do we do with these scattering parameters? How are they useful to us as microwave engineers? The key thing in all this is that the multiport device is a time-invariant linear device, and so we can apply superposition. And of course, this is the same argument that we made with respect to the usefulness of transimpedance parameters and the impedance matrix, and the transmittance parameters and the admittance matrix. In this case, if we have a situation where we have multiple waves incident on our multi-port device, we find that the wave exited or scattered from any one port is a superposition of the waves created by each individual incident wave. So in other words, if we have an incident wave of port 1 and port 2, then what comes out of port 3 is, as we talked about before, an effect of each one. If we know the scattering parameters, we can determine how much of the wave exiting or scattered from port 3 is due to the wave incident on port 1 and how much is due to the wave incident on port 2. So let's say I have a situation where we have a 4-port device and we have now an incident wave on all 4 of those ports. So none of those ports are terminated in a matched load. We have something coming toward all 4 of those ports. And what we're going to find then is, generally speaking, we have scattered waves at each of the 4 ports as well. 4 incident waves coming in, 4 scattered waves coming out. Let's look specifically at the scattered wave at port 3. We evaluate the normalized wave function B at port 3, at the port 3 location, and we get a complex number. If we know the scattering parameters of that multi-port device, if we know, for example, S31, S32, S33, and S34, we can determine how much of this exiting wave is due to, for example, the incident wave at port 4 or port 3 or 2 or 1. And it's fairly simple. If I want to know the component of the scattered wave at port 3 due to the incident wave at port 1, I simply multiply the complex value of the incident wave, the A wave, at the port plane, take that complex number and multiply it by the complex number of S31, and that gives us a complex number which is the component of the exiting wave at port 3 due to the incident wave at port 1. Likewise, for the second term, this complex number is the component of the exiting wave, the scatter wave at port 3, due to the incident wave on port 2. This gives us the component of the scattered wave at port 3 due to the incident wave at port 3, and likewise, the final one gives us the incident of the scattered wave at port 3 due to the incident wave at port 4. We can take this value and break it down into 4 numbers, and each 4 number tells us how much of that complex number is due to each of the 4 incident waves. Now, we can only do this if we know the scattering parameters. How do we determine the scattering parameters? Well, we'll talk about that later. We can generalize this result to any of the ports on a multi-port device. We'll call it port M, the scattered wave at port M. The normalized value of the scattered wave at port M is related then to the incident waves at all other ports if we know the scattering parameters associated with the scattered wave at port M. So like in the example here, we had 3, 4, 3, 3, 3, 2, and 3, 1. Here we have, M1, M2, M3, M4, all the way up to N here. So we look at this, and this sort of has echoes of linear algebra. This is the kind of thing we would see when we were doing linear algebra. Let's see if there's an application of linear algebra for these scattering parameters. First, I'm going to tidy up the notation a little bit. Again, what this tells us here is this is the scattered wave, since it's the B wave at port M. That's the subscript. When we evaluate that wave at the location on our index, which is defined, where the port plane is defined. So we stick whatever this number is into this complex function of Z, and we get a complex number. We're going to call that number BMP. All right, so it's just a number now, and what it says when you see it is, oh, this is the complex value of the scattered wave at port M when evaluated at port M. Likewise, we have this notation, a subscript NP. This is the value, the complex number, which is the normalized incident wave when evaluated at the port plane location for port N, and that gives us a complex number, which again we describe in this way, A and P. So A1P would be the complex value of the wave incident on port 1 when evaluated at the port plane of port 1. Given that simplification, we can rewrite our summation on the previous page in this form, and it's looking even more like something that we could write with respect to linear algebra. So what we're going to do is form data vectors with our complex numbers. We're first going to form the values of the scattered wave, the normalized wave values at each of the port planes. So these are a collection of complex numbers, and there are n number of them, where n is the number of ports in our multi-port device. We collect them together into one data vector. So a vector of dimension n full of complex values representing the normalized wave function when evaluated, of the scattered waves when evaluated at each port plane. Similarly, we can go through and take the incident waves at each port plane of the normalized wave at each port plane and form them into a data vector, collect them into a vector which has dimension n as well. So we have an A vector and a B vector, and again, these are simply collected values of all of the wave amplitudes for incident at the ports and the normalized wave amplitudes exiting or scattered from each of the port. Those two vectors are related in a linear algebraic expression shown here. I should have made that bigger or put it in a box or something, because this is very important. What we're saying is our vector A times a matrix S is equal to the vector B. What is matrix S? Well, based on our previous summation, you can conclude that the matrix S is formed by the scattering parameters which we have determined for this multi-port device. So this is the scattering matrix. We take, remember, we have n squared number of scattering parameters if we have an n-port device, and we can form them into a square matrix. Each element is a complex number, of course. One of the things important to notice here is each column. Notice we have in the first column S11, S21, S31, S41, and so forth, all the way down to the number of ports. I call it M here. The number of ports that we have in our device. This first column essentially is the results of our evaluation, our experiment, if you were. Well, remember, to determine the scattering parameters, we had to put a incident wave on port 1 and port 1 only. We put an incident wave on port 1, and we saw what scattered out of port 1, and what scattered out of port 2, and what scattered out of port 3 and port 4. And from those, we were able to determine the scattering parameters by a ratio of S11, S21, S31, and S41. So this column tells us what happens when we put one incident wave and one incident wave only onto port 1 only. So we put one incident wave on port 1, now the other incident waves are 0, or all the other incident waves, I should say, are 0, and we get scattering that comes out. The result of that experiment then resides in port 1. Similarly, the second port is the result of our experiment, our evaluation, when we have an incident wave on port 2 and port 2 only. We put matched loads on every port except for port 2 and put something that provides an incident wave onto port 2. Something goes into port 2, incident on port 2, and then waves scatter out of our device, out of each port. From that experiment, either measured or from evaluation, we then determine the elements of the second column in our scattering matrix. And you can see how that goes. The third column is for the experiment where we have an incident wave on port 3 and port 3 only, and so forth as we move down the line. So each column is very important in the scattering matrix. They are the result of one analysis, one measurement, one incident wave on one port, and evaluating the scattering waves that come out of all the others. Before we go on, effectively what this scattering matrix does, when you think about it is a matrix representation of a reflection coefficient, gamma n. Just like the input impedance for a single port device is a scalar value, but we sort of extend it to a multi-port device when we use the impedance matrix or the trans impedance parameters. The input admittance for a one-port device is a scalar value, but we extended it to a matrix representation by using trans admittance parameters. And again, in all those cases, just as here, the matrix itself is a n by n matrix square, where n is a number of ports. And in each of those cases, each column represents the result of an experiment, of analysis. I put a current on port 2 and port 2 only, putting open circuits on all the other ports, and then I measure the open circuit voltages, and that gives me all the trans impedance parameters of the second column. Or I put a voltage on port 3 and port 3 only putting short circuits everywhere else, and then I determine the short circuit currents at all the other ports, and from that I determine the third column of the transmittance matrix, and so forth. And so there is very much a parallel between the impedance matrix, the admittance matrix, and the scattering matrix in terms of how we form them and what they mean. And I tried to write these in a way that if you go back and look at the impedance and the admittance and you understand those, that hopefully you can see the extension and the similar logic that's used to come up with the scattering matrix. They're very different matrices, but there is a lot of underlying logic and understanding about how we form them and what they mean. Again, in this case, what we're doing essentially is extending the single value, a scalar value of a reflection coefficient, input reflection coefficient of some single port device. We're extending it into essentially a matrix form. I kind of wish we had used gamma for the scattering matrix as opposed to S, but the standard convention is to use the value of S. So one of the things we talked about with respect to the impedance matrix and admittance matrix is that it fully characterizes a linear time invariant device. Once we know the impedance matrix or admittance matrix, we really don't need to know what's inside the blue box anymore. We have all the things that we need if we wish to determine anything external to that device itself. Any voltage, current, power, whatever we want, we can insert it into a circuit and figure out the answers with knowledge of the impedance matrix or the admittance matrix. But I put a caveat and tried to make sure you understood that the values that we have to fully characterize it need to be across all frequencies. We can go through, and it's easier obviously to determine the impedance matrix or the admittance matrix at one specific frequency. It's harder to do it at all frequencies. Same thing with our scattering parameters. Our scattering parameters depend on frequency. Remember, all of our analysis we've assumed time harmonic sources, sinusoids that have been on forever and will be on forever. One pure tone at one frequency. And that's what we assume here when we're forming our scattering parameters. If we change the frequency of that pure tone from 1 gigahertz to 5 gigahertz, for example, we're going to get different scattering parameters, just as we'll get different impedance, a different impedance matrix or different admittance matrix. So make sure you understand that the scattering matrix itself is very much a dependent of frequency for really any plausible, useful microwave device. In addition to the admonishment that the scattering parameters, the scattering matrix, are dependent on frequency, there's an additional statement that needs to be made that you need to understand that is not applicable or valid for an impedance matrix or an admittance matrix. Just like for a load reflection coefficient depends on both the load impedance ZL, but also on the characteristic impedance of the transmission line connected to it. Gamma L is ZL minus Z0 divided by ZL plus Z0. It depends on both ZL and Z0. The transmission, the impedance, and the transmission line characteristic impedance. The same is true for our scattering parameters. It depends both on the device itself inside that blue box, but also on the characteristic impedance of the transmission lines connected to it. We can disconnect the transmission lines and connect different transmission lines of dissimilar impedance. For example, in this case, we initially connect transmission lines with the characteristic impedance of 50 ohms in there, and we get a certain value of the scattering parameters. If we take those off and attach instead to the same device transmission lines of 100 ohm characteristic impedance, we will get different values of scattering parameters. And of course what this means is if you have a device and you know what the scattering parameters are, you need to know with respect to what characteristic impedance. How were these defined? If they were defined in terms of 50 ohms and you put some other characteristic impedance attached to it, you're not going to get the results that you might expect.